Welcome back to Neural Networks for Architects. This is a chapter about classification, and we call that differentiation, because we don't think that neural networks play the game of problem solving in reality. So we think ourselves at the edge of the universe, we picture the world and we make differences and name these things, so we don't classify these things. So it's more about categories in mathematics than classifications, because the classifications are with logic and with arithmetics. The categories are with algebra and with geometry. So let's go in a very simple example. There are only two different applications. It's prediction and it's classification. So let's start with the classification. We follow our scheme we discussed and introduced, not to get problems with getting data, not to draw them, take pictures or whatever, so, and not to curate them too much. We simply have here a function. It's called batch. So we have random real numbers between -1 and 1, and we give n of these elements, and then we say if it is less than 0.1, this is plus, classified as plus. If it's less than minus 0.1, it's classified as minus, and if it's around 0, then it's classified as 0. So this gives give you an example. 3 elements, then you see 3 elements in the plus, and here the minus and the zeros. So that's the first one, how to get batches of proper classifications. So second step is we need the training and the validation set. So small ones. I think we can make more, no problem. So we discussed that. What is this? Second chapter, set up the network. That's this. Looks like this. The input is a vector size 1. We have it here. Then we introduce a linear layer with a vector of 6. So we have 6 parameters to learn and 6 biases to add, and this is to multiply. So we add that. Then with these linear layers we can't make distinctions, so we have to introduce, we will have that later, we have to introduce an element of discretization. This is a ramp layer, and this will be this cuts the data, and where to cut this is then calibrated with the parameters here. So it's not a learnable function, but it calibrates around. So then we have a second linear layer, which has an input of 6 and the output of 3, and fully connected means 3 by 6 multiplications and 3 additions. So 21 additional parameters to get a picture of a rational picture of the world. So then we have a softmax layer, which is just putting this layer here into probabilities, and this is done with the softmax. It's you can have a short discussion of that. Look it up if you want to go for the documentation. We have a 3-dimensional vector like here. This is of any kind, and then we put the softmax layer on this vector, and then we get these numbers. So there are 2 qualities of that. The first is extreme values are kind of compressed, and the values are gathering around the center. So in this case they are gathering around, it's minus to 0.6, so it's 0.2, 0.3, they're gathering around that. And then they're calculating a difference about that in a hyperbolic, in a spherical way. So therefore, this means we interpret that now as probabilities. The sum of them have to be 1, so probability of all these names should be 1, and the most probable with 49% is that this is a minus. And we can check that with this decoder, putting it here, decoder of the softmax layer, then it's a minus because it's most likely with 49% probability it's a minus as a name for that. But behind that there's a list of probabilities, and these probabilities are always in total a 1. So there's nothing else but the 3 names. So this is how to read that. This is done with this function here. You can look it up as well. So there's an exponential to get the extremes around a center, and then you normalize it with the total, and this is a function doing this. If you want to inspect the network, for example, go with the first linear layer, then go with these weights, then we can check it like this, extract the net, the name is this, then go for 1, you see it here, weights, there the path is 1 weights, we just take it and get the 6 by 1 weights. If we go for the layer 3, then we have the weights 3 by 6. If we go here with 3, then we get these 18 numbers. If we go for the biases, then we have the values to add in our linear function provided by the linear layers. So this is how to inspect the thing, and we can ask for net of a vector size 1. This is the input. We have this vector size 1, so we can have any kind of number, and it should produce a classification. So if we go for a net and say it should be here, and we give this if we ask like this, then we see the probabilities, and it's completely undecided, so it's random. Huh? Nearly, it doesn't know what it is. Good. Now, next chapter. This is our network. Test it. Train the network. So now we expose our mechanics with probabilities. We expose it to this equality of input and output. There are 2 different views, and we expose our networks toward that and minimize and try to get an idea what might be the connection in between and operate like that. So therefore now this is a training. So we have the training set of these are the numbers the system knows, and these are the validation set, these are the numbers it doesn't know. So therefore it's not this precise with the numbers it doesn't know. It's getting better and better, and all this is a good curve. Now it's quite sure. Now I made more than 3 million examples, again and again and again, to calibrate. You'd seen it in the last chapter, how to find with big propagation, how to find the minimum. And he's doing it all the time, again and again and again, and find a proper solution. So what we get with, if we put this to all as an option, this is a kind of report on the training. And these are some parameters you can to qualify the test as a check, to qualify the training, the loss, errors. This is the net to operate with, net F, and this is how he had with the validation set. And you see there's no error in the validation set made. All the plus is predicted properly, all the minuses are predicted properly, and all the zeros are predicted properly. So this is an important matrix for classification, and you can get that with the confusion matrix plot as a measurement on the training protocol. So we got the trained network and named that netF. And the next chapter is just to run that and look how it's working. So we can ask for netF of -2, and then he says this is a minus. We can ask for the probabilities. And then he's pretty sure that it's a minus, properly trained. If we go towards then it's still pretty sure to make where to make the distinction. So he's not so sure now with the minus and with the 0. It's absolutely clear that there's no plus. I can make it shock. No. Good. And if we go here with plus, it's just the other way around. It's plus. If we go 099, it's you see, this is an error. Huh? Now he's pretty sure that it's 0. Good. This is how classification works. You see, it's always these numbers, and we need the softmax layer, and we need the decoder giving names to the most likely distinction. Good. Next, we will go to a more extensive example with contracting or prediction, and we will have an example of weather forecast in the next chapter. See you then, and bye.